Fundamental counting theorem says that if we're going to have 8 positions in the number, it's going to be an 8-digit number. We've got 1, 2, 3, 4, 5, 6, 7, 8. We've got the digits 0 through 9, which is actually a total of 10 digits. Zero, 1, 2, 3, 4, 5, 6, 7, 8, and 9. There's 10 digits there. Determine how many 8-digit numbers, so 8 positions here, can be constructed according to the following criteria. The number must be odd, must be greater than 50,000. Digits may be repeated. Okay, so if this could simply be any 8-digit number, including 0, then it could go from 0 to 999999999. But there's an easier way to do it. We can do it by each position of a digit. In order for the number to be odd, that means it has to end in a 1, a 3, a 5, a 7, or a 9, right? Even numbers would end in 2, 0, 2, 4, 6, or 8. So this is 5 possible numbers that can go in the last spot. It has to be greater than 50,000. Now that doesn't mean the first number has to be a 6. It means the first number has to be at least a 5. And wait a minute, I don't want to put the actual number there. But the first number is going to have to be a 5, 6, 7, 8, or 9. So that actually is 5 numbers. Now, if it was 50 million even, then I couldn't put a 5 here. But we've already determined that the last digit cannot be a 0. So there's no chance of it coming out to be exactly 50 million. So any 50.1 would still be larger than 50 million. Okay, digits may be repeated. So these could all be 0s, all be 1s, all be 2s. So there are actually 10 numbers that could go in each of these spots. I could have 10 there, I could have 10 there. So the number of possible numbers should be 5 times 10 times 10 times 10 times 10 times 10 times 10 times 5. Is that right? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 5 times 5 is 25. Times, this is going to be 10 raised to the 1, 2, 3, 4, 5, 6. Which should be a 1 with 6 zeros, which is a million. So 25 times 1 million would be 25 million. And that's going to be the answer to the question.